Hello, welcome to this lesson on titration. The question of the day, what is the general chemical reaction when an acid and base are mixed? Titration is the process of determining the concentration of an unknown solution by reacting it with a solution that you know the concentration of. Because acids and bases react to form neutral solutions, this is a perfect reaction for acids and bases. Well, it's not the reaction, it's actually the process. The process is titration. The reaction would be a neutralization. You do not have to do a titration in an acid-base setup, nor do you have to do it as a neutralization. That's just the most common way that we do titrations. You can see here we have these students doing a titration. They're using a tool called a burette. Here you have, and we'll get into it a little bit more, but we have the Erlenmeyer flask, and it is clear that we have an indicator here, and the indicator is going to be very helpful in the titration. We can do a titration for our purposes to find out the concentration of an acid or a base. Here we're going to run through the example of finding the concentration of an acid, and in order to do that, we're going to use a base that we know the concentration of in the titration. So thinking back to that picture of the students doing the titration, inside the Erlenmeyer flask would be a measured volume of the acid that we're looking for, or rather looking for the concentration of. So we know the volume, we know exactly how much we put in there, but we don't know what's in the solution per se. So a lot of the time we'll just do like 100 milliliters or 250. Usually it's an amount that we're happy with, but we'll know the volume. Then in the burette, remember the long skinny tube, that is going to have a base in there that we know the concentration of, and we are going to drop the base into the flask until the indicator has changed color due to the addition of that base. On the burette, remember there's a bunch of measurements on the burette. We'll know the initial measurement, like the initial reading, and then we watch the Erlenmeyer flask and then cut the flow. And with that, we'll take a new measurement of how much base was used. Subtracting those two values, we'll get the exact amount of base that we have dropped into the Erlenmeyer flask. And we're going to use this equation. MVA equals MVB. M stands for molarity, and V stands for volume, and the subscripts are really just A and B for acid and base. Like I said before, you can do this exact same thing for finding the concentration of a base. You would just flip-flop the locations of your solutions. So here we are with a nice picture, kind of putting together everything that I just shared with you. So inside the burette, we would have the base. We know the concentration of the base, so maybe it's, a 5 molar solution or a 1 molar solution or a half molar solution of the base, and the volume we are going to figure out in the literal process. So you can see here we have a reading right here. We're going to use the base until maybe here, and then we're going to take the new reading and subtract the two values to figure out exactly how much base there is between the end point and the start point. Now the acid, we don't know the concentration of that. We're going to do calculations to figure that one out, but we do know the volume because we would have measured in a graduated cylinder exactly how much acid went into that Erlenmeyer flask. A lot of this looks like it's a hot plate. A lot of the time, hot plates, at least the nice ones, they have a magnet in there. So you can plug in this hot plate / stir plate, and you put a little magnet bar. It almost looks like it's a pill, and it goes inside the Erlenmeyer flask, and when you turn on the stir plate, a magnet inside the plate spins. You can't really see it because it's underneath this plate, but then that will cause the magnet in your solution to also turn. So as the base is dropping into the acid, the magnet is spinning them to stir the entire solution, so your acid meets base very quickly, and your indicator will have a really great time really just seeing the acid mixed with the base, and you can watch the pH change pretty quickly. There is some specific language to a titration, and unfortunately they sound kind of similar. So the equivalence point is where the acid and the base are neutralized. So for, let's say, HCl and NaOH, they're each offering one acid ion and one base ion. The equivalence point should be 7. That's where the acid and base are going to be neutralized. Let's say we were doing H2SO4, which has 2 hydrogens with NaOH with 1 hydroxide. That'll kind of neutralize twice because there's 2 hydrogens. So you can have more than one equivalence point. I am fairly certain that for the purposes of a first-year high school chemistry class, you are working with 1 equivalence point. But just know that it can go far beyond what you are going to be doing in your first-year chemistry class. So the equivalence point is the reaction. It's based on the chemical reaction when your acid and base are neutralized. The endpoint is where your indicator changes color. The idea is that you want your equivalence point and your endpoint to be the same. This way, you know that the acid or the acid/base, they're neutralized at the same time that the color change happens, because that's going to give you the most accurate data. Now, that means you have to strategically pick a indicator based on the equivalence point of your solutions. So a lot of the time, we're just going to use phenolphthalein because if you remember from the indicators video, I can link that in the description of this video, that changes color somewhere between 8 and 9. So a lot of the time we would have acid inside of this beaker, or inside of this flask rather, and drop base in. Phenolphthalein is going to be colorless in acid, but it turns pink in base. So as you drop the base, you're kind of going up the pH scale. So you're an acid and you're creeping closer and closer and closer to basic. Once that phenolphthalein changes color, you know that you are no longer acidic, kind of encroaching into the basic territory, usually not so far in. So you got to strategically pick an indicator. Additionally, you have to do your titration very, very, very slowly so that you don't pass the endpoint. Because once you get this really bright, hot pink, it means that you're like pretty basic. You want it to be the palest, palest, palest pink that you can get. So the idea is that, at least for me, I did quite a few titrations in my quantitative analysis classes. What I would do is do multiple trials, which you absolutely should do regardless. If the experiment called for 3 trials, I would probably do 5 on my own. So I would run a first trial and like kind of sloppy just to figure out where my endpoint is, just to get a rough idea. This way I can get really strategic on trials 2, 3, 4, and 5, which really are just like the real ones. The first one's kind of just like a test. I would say in my conclusion, of course, that I did a speed run, but I wouldn't necessarily use that for my calculations because I knew that I did it sloppily. So it would have been an outlier. But I would do the speed run, kind of figure out where the endpoint should be. This way, if I knew like, okay, the endpoint, you hit it around, let's say 35 milliliters, then I would know, okay, once I hit like 27, 28, now I need to slow down and be really strategic and careful with it. Because sometimes it is as close as even a half drop of base can change the color of your indicator. So in order to get a half drop, in case you were interested, this piece right here is called the stopcock. So you would open this, so you hit it vertical so that the flow can go through. And as you go from straight up and down to side, it slows down, and totally side to side flat is turned off. So if you get it and you can get a drop to just dangle, but not actually fall in, and then you lift up the Erlenmeyer flask and touch it to that drop and it hits the glass and then it runs down the solution, then you can pick up your flask and swirl it. Use a flask because it's perfect for swirling. That's literally what they're designed for. You can get a half drop, and that can even change the color of your indicator. That could be the endpoint. So again, if you want to get crazy about it, you can do the speed run and then get a rough idea and then do it very nice and beautifully. But most of the time you do multiple trials just to make sure that your data is coming in really, really great, because you want to get as close as possible. But if you pass that endpoint, it's over. You got to throw out the whole thing and start over because you don't know the concentration of the acid. So you would have to, it would be a lot. So if you pass the endpoint, you just throw it out and start over, which is another reason why I would do the sloppy run. and then do a few nice ones from there. So like I was mentioning with diprotic acids and the like, if you have an acid that provides 2 hydrogen ions like H2SO4 or a base that has 2 hydroxides like calcium hydroxide, you need to account for that when you're trying to neutralize your solution. So what I like to do is put that directly into the titration equation when I'm doing the math. So if you had 2 hydrogen ions but only 1 hydroxide ion, you have to include a 2 in your titration equation to account for the fact that you have 2 hydrogen ions here. If you were working with a triprotic acid like H3PO4, you would throw a 3 into your titration equation. If you had 2 of each or 3 of each, then you don't have to worry about it because they would cancel each other out, right? This is still algebra. So if you have the same thing on both sides, then you can cancel them. Just while we're here, M and M are not necessarily the same M. This is molarity of the acid and this is molarity of the base. So they're not necessarily the same number. So don't think that you can just cancel the whole thing and not do math. But if you had 2 hydrogen ions and 2 hydroxide ions, 2 is absolutely equivalent to 2. So you could cancel them. You don't even have to add them. If you had H3PO4 and MgOH2, a triprotic acid, and a base that offers 2 hydroxide ions, then you plug in a 3 and a 2. Okay, I know that's a lot. There's no need to memorize it. If you are feeling unsure, you're not totally confident, just write out the chemical equation and check out the mole ratio because that'll give you the answer, what numbers to add into your titration equation. All right, that is everything. I hope that when you do your first titration, you rock the house. I think they're so much fun. They're like one of my favorite lab processes ever, which is a thing only a chemist says. Please make sure to subscribe so you don't miss the next lesson. Leave any questions you have in the comment section below the video, and I will see you in the next one. Bye.